Let's look at reduce specific actions. Since in our example we have two partitions here, therefore we have two reducers. Whenever these partitions are created, the map task sends the mapping information to the task tracker on its node. This mapping information is communicated to the task trackers on reduce side via heartbeat protocol. That is, the task tracker on map side during its heartbeat protocol sends the mapping information to the job tracker. Then the job tracker sends the mapping information to to the task tracker on each of the reducers during their respective heartbeat protocol. This is how the reducers know which machines to fetch the data from. So let's look at different phases at the reducer side. The first phase is shuffle or fetch, wherein the reducer has to fetch the partition that is assigned to him uh, from each of the mapper. That is, the second reducer has to fetch the second partition from first mapper, second partition from second mapper, and the second partition from the third mapper. Okay, we'll just look at one particular case, that is, we are trying to fetch the second partition from the third mapper. So the reduce task has already been started. In this reduce task, you first check whether the mapred.job.tracker property is set to local or not. That is, we are trying to check whether we are running the MapReduce on a cluster on or on a local machine. If you are running it on a cluster, then the reduce task first creates an object of class reduce copier. Inside this reduce copier, there is a method fetch output which does the actual copying. Inside this fetch output method, you first create the map output copier class. Okay, this map output copier performs the copying from a respective mapper via HTTP protocol. Okay, so that is, the map output copier first makes an HTTP GET request to the HTTP server that is running on the task tracker side, uh, which the HTTP server is created on the task tracker during its creation or initialization. So it makes a GET request to the map output servlet running on that HTTP server, and then this servlet sends the partition to the map output copier. Okay. The number of copying is controlled using two parameters. Uh, in our example, this reducer has to fetch partitions from three mappers, so ideally it will have to run three map output copier. But if we do too much copying, that is, if there are too many mappers and too many reducers trying to do copying at the same time, there will be a network congestion. So that is why we use these two properties to control or mitigate the network congestion on a MapReduce cluster. The first property is mapred.reduce.parallel.copies, which controls the number of map output copiers that are created in a reduce task. So only this many map output copiers can copy the partitions in parallel. By default, this property is set to 5, so we can only copy the data from 5 mappers on a given reducer. There is also a property that controls the number of clients this HTTP server on the tracker sites will service. This property is tasktracker.http.threads. By default, the HTTP server only services 40 clients. In MapReduce 2, this HTTP server will be replaced by Netty, and this property will be replaced by 2 times the number of processors that are running on the task tracker at the map side. So now we have the partition, that is, we have copied the partitions via HTTP protocol. Now we have to decide whether to keep the partition in memory or on disk. Okay. If the map output size is greater than the RAM manager's map single output, then you put it onto disk. Or if it is less than the shuffle RAM manager's map single shuffle limit, then you keep it in memory. This value, that is max single shuffle limit, is computed using this formula. That is, you use a certain user-defined threshold. Uh, you multiply that threshold to the amount of memory allocated to that reduced task, and you also multiply a constant 0.25, that is, which specifies that for a given map task, you can only get 1/4 of the memory that is allocated to the entire reducer, to the buffer of the entire reducer. Therefore, it's multiplied by 0.25. The threshold is specified using the property mapred.job.shuffle.input.buffer.percent. By default, it is assigned value 0.7. You can check whether a given partition was copied onto RAM or was copied onto disk using by looking into log file. That is, there will be an entry shuffle some bytes into RAM or shuffle bytes into local-fs, which means that it was spilled onto disk. Inside the fetch output method of reduce copier, it starts two threads. First of class inmem fs merge thread, and second of class local fs merger. Okay, the first thread does the merging of the map output as they are copied in memory, and the second class does the merging of the output that were spilled onto disk, uh, and of course it does the merging onto disk. You do the in-memory merge if one of the two conditions are met. First condition is if the um, memory that is used by a given buffer is uh, is is over certain threshold. That is, the threshold is specified using property mapred.job.shuffle.merge.percent, and the default value is 0.66. That is, if the buffer is used, the memory that is used for a given buffer is about 66% of the specified allocated memory, then you perform an in-memory merge. Or if the number of map outputs, okay, are greater than certain threshold, then you perform an in-memory merge. This threshold is specified using property mapred.inmem.merge.threshold. By default, its value is set to 1000. Similarly, you perform an on-disk merge, which is also called as interleaved on-disk merge, if the number of files on the disk is greater than certain threshold. This threshold is specified using property io.sort.factor. This property is same as the property on the map side. That is, this property controls both the on-disk merging at the reduce side as well as the on-disk merging at the map side. For example, if there are 50 files and io.sort.factor is set to 10, then there will be 5 rounds of merging, and in each of those rounds you'll merge 10 files at a time. The merging logic is slightly more complicated than that, wherein it tries to minimize the number of merge file it has to do, but we'll not get into that. Okay, so now that we have performed merging in parallel, we have to merge this. We have to merge this some of the remaining in-memory files onto disk. Okay, that is, we spill the in-memory data onto disk. This is done because MapReduce framework assumes that the user reduce function needs all the RAM it can get. which if you are writing a simple reducer, okay, which does not need that much RAM, okay, then you are essentially wasting the cycles for writing onto disk. So you can tweak this behavior using the property mapred.job.reduce.input.buffer.percent, which is by default set to 0. You can set it to 0.7 if your reducer just performs a simple operations like aggregation or just summing up over the values, So once we have the data in a format that we like, then we create an iterator over that data. This iterator is a form raw key value iterator, and then you call the user defined reduce class. So this concludes the reduce specific actions. Then finally, inside the commit phase that we talked about earlier, the framework copies the uh, data onto, usually inside HDFS.